All right, so if you want to take a second and read over the scenarios so we can talk about it and you'll know what I'm talking about. So we have a college student that's spending a summer in Seattle. They're going to save some money for the trip, and they've kind of budgeted out to be spending about $400 a week. And so the natural question that arises here for me, if I'm thinking about this scenario, is when am I going to run out of money, right? Like how long is that money going to last me for my trip in Seattle if I'm spending on average $400 a week? And so in order to answer that question, we're going to write a linear model. And then there's a bunch of other questions we can answer too. So we're going to write this model looking at how much money is remaining. So just like we did before, there are a certain set of important things that we need to know when we're working with these functions, right? So we want to talk about, what's the input here? What's the output? What's the initial value? And what is the rate of change? And then finally, are you increasing or decreasing, which we'll just kind of incorporate that question. So if you notice, these are the same questions that I was asking when we were working with graphs and equations and all that on whatever Monday. And so this is the same set of questions because for a linear model, you have these components. And once you identify those components, then, you're moving. So the input for this, you have two changing quantities, right? So the two quantities that are changing, you have time in weeks. How did I know that I should do this in weeks?
It says per week.
Exactly. That's what we're talking about. We're talking about a changing quantity that changes every week. So we're going to express time in weeks. And then you have another changing quantity that we decided that we were going to look at, which is how much money is remaining, right? Money left. So these are the two things that are changing. And that's going to determine what your inputs and outputs are. So we're going to input the time because the amount of money left depends on the time. So that's how I can determine that input-output relationship. So this is money left. And so then there's an initial value. At the very beginning, how much money is left? Well, that's $3,500. How is this quantity changing? It's going down or decreasing by $400 a week. So the rate of change is negative 400. This function is decreasing. Okay? So you see how I already have literally everything that I need. So we can rename this, we'll call this T. That's easy, right? T is for time. And the money left, we'll call that output M. Does that make sense? You can call it Y if you want to. You can call it whatever you desire. I'm just going to choose M for money. And recall with our function notation, from these two things, we're going to have a function that is the function M in names of the output as a function of T. So we're going to write this function as M of T. Money as a function of time. And then we're going to use the old faithful Y equals mx plus b linear model because all linear functions can be written in this format, where M is the rate of change, negative 400, times T, the input variable, plus the initial value. And there is your linear model, all done. Okay. So you have to look at what's being asked, the scenario, make sense of it. I know that it's decreasing because I've defined the output of the function as the money I have left. You could also write another one for money spent. What would be the initial value for money spent at time zero? Zero, right. So that function is going to describe the same thing. It's just the quantity that you're getting spit out is different because you're asking a different question, right? So it's important to understand kind of in general how the scenario works. And if you define input, output, initial value, rate of change, all of those things will make more sense to you instead of just trying to jump directly to writing an equation. Okay. So again, just like we did on Monday, you have these four basic components. And once you determine those, this becomes a lot easier. Okay. So you're training yourself to look for these things by understanding what they are. And then you can pull them out of this better. What you do not need to do is just go start pulling numbers and putting them places. If you're not making sense of the situation, this becomes difficult very, very quickly, okay? Here are a lot of words that describe exactly what I just told you. Notice in number 1, we identified the two changing quantities, time and money remaining. I defined a descriptive variable, M and T. I carefully read the problem, found the slope or the rate of change in the initial value. Then I read it again and I'm like, what are we even trying to figure out here? And then we just continued in this process. So if you need a reminder, here is a reference for you from the textbook. So sometimes we give different information, like depending on what the problem gives us, we're going to do different things and we'll start in different places and we may end up in different places. But if you rely on the fact that you basically need an input and output, a starting place and a rate of change, then this will be a lot easier to get to. Okay. So let's look at this scenario. Hold on, let me find it. Okay. So let's say that a girl named Hannah plans to pay off a no interest loan from her parents. Her loan balance is $1,000 and she plans to pay $250 a month. Loan balance, payments of $250 a month until the balance is zero. So let's go ahead and just start doing this. So this is, we have an input, we have an output, we have a rate of change, and we have an initial value. Okay, so the loan balance is $1,000. I'm thinking that's going to be the initial value. This relationship has two changing quantities. We have the loan balance, because we know that's going to be going down as time increases, right? And we have time elapsed. Time is going to be expressed in what unit? Months, because it says that, right? Per month. Okay, so one of these is going to be the input and one of them is going to be the output. Well, the loan balance depends on the time that's elapsed. So the input is time.
Is time always an input?
In general, yes, because when we're modeling these things, we usually want to know what's happening over time. Right? And remember, your input always is increasing, which makes sense because time should always be increasing. So, so output is going to be the loan balance. So as time increases, what's happening to the loan balance? It's decreasing. So this is a decreasing function. She's paying $250 a month. That loan balance is going to decrease by $250 for every increase in the time t. All right. Let's go again. Let's figure it out. So this is going to be, we're going to call this time is t. And we can call this, b, whatever. Like I'm just going to call it balance. And so from there, we can write the function notation, b as a function of t. And then the rate of change is the slope times t, the number of months, plus $1,000. Because when time is zero at the outset of our scenario, if we plug in a t of zero, what is the loan balance? $1,000. That makes perfect sense, right? And so if t is 1, she's made one payment, so the loan balance increases by $250. Okay, so 1,000 minus 250, that's going to be $750. So she has $750. Does that make sense? Questions so far? That is how the process and the information I need is the same every single time. And we can reduce this to a very simple, repetitive situation, even though all the numbers and all the scenarios are different. They all share these common features. And if we can learn to train ourselves to find those things in the context of a linear model, then we're going to be cooking with grease every time. Okay? Cool. All right. Next time, I'm going to give you something different. In this example, I'm going to give you input-output pairs. Okay? They're not, these are like the easiest ones because they straight up give you everything. Here are your reference points if you need to look back for what I'm about to do. Okay, so in this example, the town's population has been growing linearly. That immediately tells me that I'm going to use this to write a model. So then in 2004, the population was 6,200. In 2009, the population has grown to 8,100. So let's go ahead and make our little list here. Input, output, rate of change, initial value. Let me do something. I'll need some more space for this. All right. All right. So again, we have this instance where time is going to be one of the changing quantities, right? So we're going to be changing in what unit? Years. And then the other thing that's changing is the population, right? So one of these is going to be the input and one of them is going to be the output. What's the input in this case?
Time.
Time. Beautiful. Therefore, the output must be the population. Right. So what are these numbers that they're giving me? I'm not given a rate of change. I'm not given an initial value, but I am given two pairs of time and population. So this is two coordinates that they're giving me. It's a two input output pairs, right? So I'm going to have, let's define this. This is going to be t, and we'll call this p, and the function will be p of t, right? So the first thing I'm going to do is I'm going to be like, all right, well, I've got two coordinates here. I've got some time values, and I've got some values for population as a function of time, right? So in my mind, you can express these as coordinates. I just like to write it like this because it keeps it easier for me to look at. So 2004 is the first input, and in that year, our population was 6,200. And then we have another one that's 2009. And here we've grown to 8,100. So I'm going to show you a trick now, okay? And this trick is going to be useful to you anytime you're working with years and large inputs, because that's not very fun. You can do this from here if you prefer, but I'm going to show you a shortcut. And you might not realize you can do this, but you can. So first thing I'm going to do is when I'm working with inputs that are this large, think about the fact that I'm going to need that t-intercept or the y-intercept, right? And that's going to be where t is equal to 0. So if I'm trying to backtrack to where t is equal to 0, we're a long way from 0, right? Does that make sense? So if I'm trying to back this thing up to 0 to find that t-intercept, I've got a problem. So all I have to do is redefine t to no longer be the year. I'm just going to define t to be the years since 2004. So year 0 is 2004. So what would year 2009 be? What is it?
Year 8. Or sorry, I
There you
can't
go.
math, it's too early.
That makes sense? Okay. It's all right. So like in your mind, what you can do if you're not quite tracking that is you can be like, all right, this is 04, 05, 06, 07, 08, 09, and this is 0. So this is 1, 2, 3, 4, and 5. Now, aren't those numbers so much nicer? I've just changed the way I've defined the input variable. So instead of years since like year 0, now I've just shifted everything up. And you can do this with linear functions. Okay? You can always make that shift to where you make the first one 0, and then we're just counting up from there. So do you agree that 2009 would correspond to 5 years since 2004? Make sense? Okay. This will work if you calculate with those big years. If you don't like this, then don't do it. But it's going to make your life a whole lot easier because look, where is my t-intercept? What's my starting value? 6,200. There it is, right? So the initial value for this is going to be 6,200. And the rate of change, well, we have 2 points, right? This is essentially a coordinate. And we know how to calculate rate of change. That is change in y over change in x, which is essentially, in this case, the change in p of t over the change in t, right? So this would be 8,100 minus 6,200. And then this calculation is quite simple. So 8,100 minus 6,200, I don't remember what that is. Hold on. Did I already do it? I wrote it down.
Negative 900.
Nope. What is it?
Negative 900. What would it be?
Shouldn't be negative. It should be positive.
Oh, wait. Yeah. 1900.
1900.
1900. Thank you. I don't trust myself to do that in my head. All right, and then 5 minus 0 is simply 5. Notice if you had left the input variable defined this way, when you calculate the slope, what's 2009 minus 2004? Still 5. Right? So you're still going to end up with the exact same stuff. That's why this works. Because it's still, the difference is the same. And so all of your other calculations would be intact. And once you got to this point, you just made your life a little easier by intelligently choosing to do something, which you can always do in this case. All right, so let's write the function. Now, and then, this is done. 1900 divided by 5,
380.
380. Thank you. It's 380. Let's double check. Let's make sure that our rate of change numerically matches up with this situation. How is the population changing? Is it increasing or decreasing over time? So we should have a positive rate of change, and we do. So we're going to go ahead and write the function. This would be P of T. Population is a function of time in years. It's going to be equal to 380 times the number of years plus 6,200. Okay? So notice I still haven't started answering question A or B, right? And remember in the very beginning, I said we need to construct a model in order to answer questions about a scenario. So your first step, if you see a question like this, is always going to be to construct that model first. And then we will use this tool to do certain things. So predict the population in 2013. So year is 2013. But our input variable is in terms of time t, years since 2004. So in this scenario, t would be equal to what? Well, you could continue this little thing over here if you want. Yeah, you can continue this if you want. Or you can find a pattern and just recognize that, this is moving up by a certain amount, right? So it's just minus 4. Do you see how that's working? Do you see the pattern and how to switch things over from year to t? 2006, you just subtract 4 from this one because 7 minus 4 is 3, 8 minus 4 is 4, 9 minus 4 is 5. And so then you can continue that pattern just by making sense of it. Or you can just continue this list out, whatever. Does that make sense? Do y'all see how I'm doing that? Yes. All right, so t is 9. Guess what? All I have to do now is evaluate the output for this function at input 9. It's going to give me the population in year 9, which is 2013. So we'll do that. We'll say, okay, well, what's P of 9? 380 times 9 plus 6,200. This is equivalent to adding 380 to 6,209 times. But, multiplication makes things easier. Times 9 plus 6,200. Y'all double check me. I got 9620. So the population in 2013 is predicted to be 9,620 people. Notice I answered in context because the problem was given to me in context. Okay. All right, so now we want to identify the year in which the population will reach 15,000. So let's think about this. Identify the year. So I'm looking for an input or an output. Am I looking for a T or a P of T here? The year is P of T? P is population. I'm looking for a T, and I'm given a population, which is P of T. Y'all see what I'm saying there? So you see how it swip-swapped what it gave me and what it's asking for? This is all the way back to chapter 3. When I asked you to evaluate, and then I asked you to solve for a particular value of the input variable. This is the same thing. All right, so what am I looking for now? All right, well, I'm trying to find T, P of something. Let's rewrite the model. and then input what I'm given. So it gives me a P of T of 15,000. So guess what I'm going to go do? I'm going to go take out this and I put this here instead. And then look, I can just solve for T with the miracles of high school algebra. It's all about figuring out what they are giving you and what they are asking for. And then you can use the mathematical tools that we just like we've been doing this for years, right? So, you'll subtract 6,200 from each side. That's 8,800. Then we'll divide both sides by 380. 23.2 years. So what we interpret this to mean, remember, we define the input variable T to be years after 2004. So this would be 23.2 years after 2004. And so to determine what year that's in, 2004 plus 23.2 years is going to be something. 27.2? Actually, that'll be 2027.2. So this is the actual year. So sometime in 2027, the population, what was the question? I don't even remember.
Identify the year in which the population will reach.
So sometime in 2027, the population will reach 15,000. And that's that. But notice how I had to jump back out of this weird so we would interpret this to be 23.2 years after 2004, and then you need to go back and tell me what year that happens. Make sense? How did I know I needed to go back to the actual year at the end instead of the years after? Well, look, yeah, identify the year. It doesn't say how many years after. It says identify the year. So I'm going to have to make sure I understand what I'm talking about, what these numbers mean. Because you're not going to tell me that in the year 23, the population would reach 15,000. That doesn't make any sense, right? The year 23, that's wild. People didn't have running water and electricity back then. All right, I want y'all, in your notes, I'm going to put just the answers up for this one because I want to be able to kind of see you do this in real time because it's typically difficult for people to think about. It's one of those things where it looks easy until you try to do it, and then sometimes it gets kind of hard. So I want you to do this one. And I'm going to write just the answers up, and then I want to see how we're doing, and I want to take questions and anything like that. I'm just going to walk around and see how you're doing. Let me put your answers up for you. I'm not going to write the interpretation up there because then that just takes all the work out of it for you, right? We'll talk about it in a second. But I asked you a question, right? I'm like, what is going on here? And then we need to know what that y-intercept is actually telling us, right? So, again, as you work through this, hopefully you were like, all right, what are the changing quantities that are happening here? Number of donuts is changing, and the cost is changing, right? So one of these is going to be the input, and one of them is going to be the output. So the cost depends on the number of donuts. So this is going to be the input, and this is going to be the output. then I'm going to have an initial value and I'm going to have a rate of change. So if the output is the cost, that's what I'm talking about here, right? I'm talking about cost. So what's the initial cost? Well, with no donuts sold, we got a cost of $25,000 because those things occur. They got to pay the rent, the insurance, and the power bill and all that, even if they don't make any donuts, right? All right, so what's the rate of change for the cost? Well, the additional cost above and beyond all this stuff increases by 25 cents for every donut they make. This is an increasing function with a positive rate of change. And then we just go down here and we're like, all right, well, this is going to be mx plus b. So C of x is the rate of change plus the initial value. The y-intercept occurs here at 0, comma b from the equation, right? And what does that mean? Well, you have to go back and understand what this x and this means. This is the input. This is the number of donuts, and this is the cost. So the number of donuts produced at the y-intercept is 0, and the cost is $25,000. And so we can take this little bit of information and we can say, okay, well, if they produce, let's talk about that in words. If they produce 0 donuts, they still incur a cost of $25,000. So see how I went on these little waypoints? I have to translate in and out of the mathematics and the actual understanding and interpretation in the context of the problem and the question of what's going on here. And the way I do that is by reminding myself what the heck I'm talking about. So if I have 0 this means nothing. But if I remind myself, and I like to write it down because I get lost, this is the number of donuts and this is the cost. So when they have made 0 donuts, they have a cost of $25,000. And then if you're following that process, this becomes a lot easier. Okay? If you don't know what the numbers mean, you just stab it in the dark and it's not going to work out. Okay? Don't be stabbing in the dark. Actually write it down and tell yourself what you're talking about. Questions on this one? Cool. Do the try it number 2. I'm not going to put no answers up right now for this one. We did an example very similar to this one if you need to look back. I'm going to give you we'll start with 5 minutes. And I'll see how we're doing, and then I'll put the answers up. We'll talk about it. I'll answer any questions, and then we'll move on. Maybe 5. Alrighty. 5 minutes. yelling? Do y'all like hear somebody like excitedly talking about something? It must be Mr. Freeman. 'Cause I know it's not Mrs. Slay. Say who that is. Do you hear them? Don't I hear them like howling? Maybe it's a video. I don't know. Weird. How we doing out there? Double check your stuff. Make sure you got what I got. Good. Question. Question. All right, so for this one, it's growing linearly. I've got two input-output pairs. I can already look at it and tell. I've got 2008 and 28,200, and I've got 2012 and 36,800. I don't want these to be 2008s. I want that to be 0. We're going to define the time or the input to be time after year 0 or 2008. So this would be 4. Much easier. So the intercept is 4. No. I don't know what I was thinking here. Intercept is 28,200. Stop. And then the rate of change I've got to calculate, right? So I've got to do the slope formula, the change in the output divided by the change in the input. And you'll end up with some slope. I don't know. 36800 minus 28200 be 8,600 divided by 4. And give me 2150. Is this function increasing or decreasing? Well, the output is the population, right? So that's growing. It says growing. So that's valid. So we'll say, okay, well, population as a function of time is going to be 2,150 times t, the number of years since 2008, plus 28,200. Predicting the population in 2014 would be P of, what's the trend here? So like 14 minus 8 is 6. Yeah, so this would be P of 6. And I know that you can evaluate a function. I'm not going to do that. And then identify the year in which the population will reach 54,000. That means that P of t, the output, is 54,000. And so we would just rewrite this, replace it with the known value, and then we would solve for t. And then you just go back and recalibrate your year. Okay. You get t equals like 12, right? And so 12 years after 2008 is 2020. Questions? Not my thinking. Okay, fabulous. All right, you're not going to like this one, but I love it. So using a diagram to sketch a model. So if you've ever had a class with me, especially the pre-cal class, not so much in stats, well, I guess in stats, that I will harp on you until like the end. Draw a picture. Okay, so sometimes in a scenario, you're going to have to draw a diagram to get a better idea of what's going on. In the previous questions, there wasn't really like a diagram to draw, right? It's basically just what it is. But sometimes we have to draw some sort of geometric shape just to get a handle on how the quantities are changing. Right, and that's what we're going to do with this one. So There we go. All right. So we have these two people. They start at the same intersection and then they walk. What is it? Then they walk in two different directions. They are communicating with a two-way radio that has a range of 2 miles. How long after they start walking will they fall out of radio contact? This is a very complicated question. Okay? So we just leveled up. The first ones were very simple. This one is not. So let's start thinking about what's actually happening here. And I mean, I'm talking about direction and distance and all kinds of stuff. So I'm immediately like, well, let me draw a picture and try to figure out what's going on. So Anna's walking east, Emmanuel's walking south. So first let's get a handle on what that looks like. North, south, west, east. Good? All right, fabulous. So if they are starting at the same intersection, let's say that's here. They're both starting here. Anna is walking east. That is this way. She's going 4 miles per hour. Emmanuel is walking south. That's this way. He's going 3 miles per hour. All right, so let's go ahead and start picking apart what we've got going on here. And we've got two different situations, right? We've got two different linear functions. We got one for Anna, and we've got one for Emmanuel. So I'm just going to go over here and start organizing some information. So I'm looking for input, output. Notice this is still turning into the same idea that I had before. I still don't know where I'm going yet, but I do know that this is a good starting spot for me. Okay? So what is changing when they're walking? Time. I know to consider the time because it gives me a rate in miles per hour. So what's changing? The miles and the hours. Okay, so which one is which? Is the input's going to be the time, and the output is actually going to be the distance, which is what miles are, right? Okay. So the initial distance from the starting point for Anna is going to be what?
0,
Yeah. What about for Emmanuel?
1,
0. The rate of change of that distance for Anna is 4 miles per hour. For Emmanuel, it is 3 miles per hour, right? As they walk, is their distance from their starting point increasing or decreasing? Increasing, so those rates of change will remain positive. All righty, so we're going to define time. Time's going to be the same for both of these guys, right? Does Emmanuel experience time differently than Anna?
No.
No, so they're both going to be t. But the distances they've traveled as a result of that time, will those be different? Yeah, they're going different speeds. So let's just call this one A of t, and let's call this one E of t. These are outputs, right? I've chosen A for Anna and E for Emmanuel just to keep myself straight. All right, so I got a function happening here, and I got a function happening here. I have two lines. I have two linear relationships. Okay, so here, let's go ahead and write this one. These are linear models, so we're still going to use mx plus b. So let's write one for Anna. A of t is going to be slope 4 times t. Initial distance is 0, so that's Anna's distance function. Emmanuel's distance function is going to be E of t equals what?
3,
3t. Rate of change 3, input variable t. Does he have an intercept value that I need to put on there? No, initial 0. All right, cool. So now there is actually a third changing quantity in this particular thing. So Anna's distance is changing, Emmanuel's distance is changing, but the other thing that is changing, remember, we're talking about the range of 2 miles. That means how far they are from each other, right? So we have the distance from start for Anna, the distance from start for Emmanuel, but we also have this third quantity, distance from each other. Does it also depend on the time elapsed? Okay, let's just define this output. Let's do this. So input is still going to be t. The output, let's define a new one just called distance. Distance from each other. The rate of change here, I don't know what that is. What's the initial distance apart? 0. They're standing in the same spot. Right? It says that. They start at the same intersection. So we're going to define this to be d of t. Okay. So what you're going to have to recognize here is, what shape are you looking at?
Triangle.
What kind of triangle?
Right.
Is there any relationship that will relate those three quantities together?
A squared.
The Pythagorean theorem. So it's the square of one leg plus the square of the second leg equals the square of the third leg. And so what will relate that is going to be d of t squared equals e of t squared plus a of t squared. So now I can obtain some information about d of t, because it's going to be a direct consequence of how a and e are changing. So we have this third quantity, right? So, well, the cool thing here is that I know what this is, and I know what this is. So recall back from geometry and from everything else we've been doing thus far, when you have an equivalence like this in words says that these are the same thing. They're equal. Thus, they are interchangeable in the equation that I write. So I can take this out and put this in its place. That's allowed. We need to understand that that is allowed, because mathematically, I am telling you that they're the exact same thing. So we can swip swap them whenever we want to. They are equivalent. So let's do that. So let's rewrite this. I'll have d of t squared. E of t is actually 3t, right? Squared. And a of t is actually 4t squared. And now we can do some, algebra. So d of t squared would actually equal 9t squared plus 16t squared. Can I combine some like terms? Sure. They're both t squareds. This will be d of t squared equals 25t squared. And watch what I'm about to do. I would like to know what d of t is as a function. So how can I isolate and solve this equation for d of t? Yes, I will take the square root of both sides. Thus, d of t is equal to plus or minus 5t. Only one of these makes sense, because if you look, you have a linear function now, right? Is this not a linear function, a slope times the variable? What's the intercept for this? 0. So does it make sense to have a negative rate of change here for the distance? No. So we will completely ignore the negative result and we'll take the positive, because that's the only thing that makes sense. This is a distance. It's not going to be decreasing. They're not walking closer to each other. They're walking further away. And these are mathematical tools. So while both of these mathematically would give a positive and a negative, in context, the negative doesn't make sense. So we discard that tool, right? We just discard it because it don't make no sense. So guess what? Now I've got a function for d of t. And let's go back and remind ourselves what d of t is. All right, so what's d of t? This is the distance between them. right? And this is the time. So let's go back now and re-look at what the question is asking. How long after they start walking will they fall out of radio contact? How many miles apart do they need to be to fall out of radio contact? 2. So the distance needs to be 2. And the question is, how long? That's when. That's a time. Right? Does that make sense? Okay. So the distance I'm interested in is 2. And I would like to solve for the time associated with their distance being 2. And so, 2 divided by 5 is 0.4. And let's go back and remind ourselves what our units are. What are the time units in this problem? Right. So the time would be in hours. Yep. The miles is the distance part. Remember, your slope units are the output divided by the input. So it would be miles output per hour input. So we're talking about hours. So 0.4 hours. And if you want to translate that into minutes, it'd be 60 minutes times 0.4, so about 24 minutes. They're going to stay in radio contact for 24 minutes. Because I don't know about you, but I'm not walking around talking about we got 0.4 hours of class left. Because that doesn't really mean a whole lot to me, right? So if I'm going to answer your question in the best and clearest way that I can to communicate effectively, I'm going to know that I'm going to talk to you in terms of minutes. Because I swear nobody's going to say 0.4 hours. That's crazy. I've never heard anybody say that in casual conversation. 0.5 maybe. All right, so that was a lot. That one was fun. This escalated rather quickly. All right. This is the college part. So let's do another one. More geometry. I love how we fool y'all into thinking all of these are separate disciplines. Right? There's geometry, and we only use that in geometry class, and then there's algebra, and we only use that in algebra class. It's all part of the same toolbox, and sometimes we need certain pieces, and sometimes we need other pieces. All right, so using a diagram to model the distance between cities. This one's fun. You're going to love it. This one and the one previous is the one where I was like, hey, please make sure that you are skilled in everything that we've learned thus far, because we're about to use everything that we've talked about previously in the last 2 lectures in this problem. So there is a straight road leading from the town of Westboro to Agratown, 30 miles east and 10 miles north. Look at this. More of this north, south, east, west business, right? Partway down this road, it junctions with a second road, perpendicular to the first, leading to the town of Eastboro. If the town of Eastboro is located 20 miles directly east of the town of Westboro, how far is the road junction from Westboro? That's a lot of words. Okay, so let's go ahead and orient ourselves. I hate it when it does that. North, south, west, east. All right, cool. Hey, one thing you might notice is that north, south, west, east looks like a coordinate grid. Just a thought, right? So we can kind of start there. I'm going to use that tool because I could have used it in the last one.
Wait, you go northwest, southeast instead of northeast, southwest?
Huh?
You go northwest, southeast instead of northeast, southwest?
Yes.
Oh, that's
I go top, bottom, left, right because I spell we. That's how I remember. I spell the word we for west and west, east and west. Yeah.
It's like a clock, and you got every side you want.
It's wild. My brain does weird things. That's just the way it is. However you want to draw it, please feel free. All right. So I got me a little coordinate grid here. North, south, west, east, again with the weird whatever. All right, so there's a straight road leading from Westboro to Agratown. So we're gonna start in Westboro, so that's Westboro, right? The origin. Alrighty. So Agratown is where? It's east and north somewhere, right? So I'll go east and then I'll go north. So it's somewhere here, right? You see how I did that? The origin is called the origin because it's your starting place. I put Westboro on the origin because that's where I start. That makes sense? Okay. All right, so Agratown is 30 miles east and 10 miles north. So this is east. How far east did I go? 30. So X is 30. So the horizontal distance traveled. And so what's going to be the vertical distance traveled, or the Y part of this coordinate? 10 miles. There you go. So I've got a road. There's the road. That's stupid. I don't like that. I really don't like that it's not being very exact there. I'll just do my best. Are y'all ready? Okay. So there's the road. Part way down this road. Part way down the road. So notice I'm having to go back and I'm really having to think about what the heck that's talking about. So if I'm traveling on this road, part way down the road is somewhere right here, right? It junctions, and what that means is it splits off. There's a turn. This turn is perpendicular to this road. We learned what perpendicular lines look like. They form a right angle. So that's going to roughly be something like that, right? And this is a right angle. So there's other road leading to the town of Eastboro. Okay? Eastboro is located 20 miles directly east of the town of Westboro. Miles directly east. 20 miles directly east. Hold on. What I'm doing right now is I'm like sense making about some stuff because something is not looking right to me for some reason. It's probably because my slope is jacked up. Okay. 20 miles directly east. It's going to be there. So what's this coordinate going to be? 10. Okay. Why? Why? Oh, I see it. Okay, yeah. Okay, so like, just to let you in on my thinking process while I'm trying to make sense of this, what was aggravating me is that this point looks like it's further over than this one. You see how that would like kind of make me mad? Why is that happening here? This is what kind of sketch? A junkie one. You remember the junkie sketch? They were saying this like all the time, the junkie sketch, like it's just for relative positioning. If you were on a coordinate grid, you could make this look really nice and these would be in the right places. But I just had to stop for a second and be like, why is that happening? Again, it's important for you to make sense of things as you go. And I'm like, oh, okay. And then you pointed out, it's because that's kind of down here. And I just drew a sketch without any grid lines. But it's good enough for me because I have all the points and I kind of have a general idea what's going on. This is a junkie sketch. If you've never had a class with me before, a junkie sketch just gives you the information you need. If that bothers you and you want to do it on a coordinate grid, it'll look perfect. That's why I give you graphic. All right, so I've got Eastboro down here. Okay, so I've got a diagram that's outlining this. How far is the road junction from Westboro? I'm looking for this point right there. So one of the first things that you need to realize when you are working through this problem is that I'm trying to solve a system of equations. And if you remember from Algebra 1, there's a way to find the point of intersection. And that intersection occurs at the solution to a system of two equations. Okay? So that's the next trick you're going to have to pull out of your bag from Algebra 1. Okay, you have to know that that happens. And also, I have 2 lines here. This entire section is about creating models with linear functions. So guess what I need? I need a y equals mx plus b for each of these. So I need one here. I need a y equals mx plus b here. And I need a y equals mx plus b here. So for the red line, y equals mx plus b, I need a slope and I need an intercept. What is the intercept?
0,
0. Cool. What is m? Well, I'm going to have to use the slope formula to get m, right? This is 0, 0. Luckily, that makes things easy. So this would be 10 minus 0 and 30 minus 0. This would be a slope of 1 over 3. You with me? Sure. Well, the good news is I already have my linear function here that describes this line, 1/3 x. Good?
Why would you do that?
When he gets back.
Oh, no, no.
You got it? Okay. You're fine. No, good question. All right. It's such an awful question, right? But once you do it a few times, you're like, oh, okay. B. What's this one? I don't know. Let's think. What do I know here? What do I know here? I don't have 2 points on the line, so I can't do this. I don't know where that's going to hit up there, so I can't do that. Oh, wait. I can figure out the slope of this line. How can I do it? What information do I have? Right? Perpendicular. So I know how to write a perpendicular slope. This slope is going to be the negative reciprocal of this one. Yeah, so this is going to be a slope of -3. And I don't know what this is. I'm going to have to find it. I do have a point on the line, 20, 0. Remember, using a slope and a point, I can calculate the intercept. And so here I'll have 0 equals -3 times 20 plus b, and I can solve for the intercept. This will be 0 equals -60 plus b. So the intercept for this one is 60. So this function is going to be y equals -3x plus 60. So I have a model for each of these roads. And once you have 2 equations, you can solve for their point of intersection. How do we do that? We set them equal to each other. All right, so what we're going to do now, I'm going to do that in blue. I'm going to say, all right, well, where does the equation 1/3 x coincide with or equal this equation, right? That's going to be where they're in the same place. Well, that's fine. I can solve for x here. I have 1x. I can solve for it. So I'm going to move all the x's together. So this will be, plus 3x plus 3x. It'd be 9 over 3 is 10 over 3. Double check it for me. 3 plus 1/3 is 10 over 3. Y'all trust me? Y'all ain't learned nothing about me yet, have you? All right, here we go. We'll see. So 10 over 3. Well, I mean, it would be 3 would be 9 over 3. 9 plus 1 is 10. So 10 over 3. All right. So, I mean, then we can solve for x. We're just going to, divide by 10 over 3. 60 divided by 10 over 3. $18. So the x coordinate is 18, whatever this is, right? This point. It says x is 18. How do I find the corresponding y? Well, yeah. Well, I mean, this blue point is on this red line, right? And I have an x. Can I use an x to get a y? Yeah. So I'm trying to plug this in here and then whatever it gives me. I think it's gonna be 6. Right? 1/3 of 18 is 6. So this coordinate is 6. Could you also plug 18 into this and get the same y for this coordinate? No. They're gonna give you the same answer right here. Because they both have this point as a solution on the line. Why did I choose this one, do you think? It's easier. I just picked it just because it was easier. That's it. So we'll plug that back in. 1/3 of 18 is going to give me 6. Okay. Well, we're almost there now. Not quite. We've done a lot, but we know where it is. We just don't know how far. Right? Because the question is how far, right? I don't know why that's not doing that. Let me see. Give me a second. Let me push this down a little bit manually. So is there a way, using a point, can we find out how far 2 points are from each other? Is there a way that we can do that? There are a couple ways. There's a distance formula, right? Remember the distance formula? Or you can just do the Pythagorean theorem, whatever. I don't like the distance formula. You get the distance formula from the Pythagorean theorem anyway. So let's take a look. So do you agree that if I'm trying to find how far this distance is, that I can just drop a perpendicular right here and I've got a right triangle? So what's the horizontal leg here? 18. How do I know that? Well, I created this triangle from this point. How far to the right do I go to get to this point? 18. How far up do I go? There you go.
Why did you cut it in half? Isn't it already right triangle?
Yes, but that's not the one I'm looking for. I'm trying to find the distance to this point. So if you think back to pre-cal, when I was trying to find this distance, or the magnitude of the vector, I'm not worried. I don't care about any of this. All I want to know is how far this junction is from Westbrook. So this blue highlighted piece is all I'm looking at. So if I want to know how far this is from this, then my triangle's going to be right here. Does that make sense? Because that's going to force the hypotenuse to be this distance. Now it's just Pythagorean theorem. A squared plus b squared equals c squared. So we're going to work like this. We're going to say, okay, c squared, which is this guy, the distance from Westboro to the junction is going to be equal to 18 squared plus 6 squared. I mean, I don't know what that is. I don't know. Let's see. So 18 squared plus 6 squared is 360. What do I do next? Take the square root. Do I care at all about a negative distance here? No, that isn't even a thing. Okay. So 18.97. What are the units that I'm using here? Miles. So to answer the question, how far is the road junction from Westboro? 18.97 miles away. Alternatively, let's see if I can remember the distance for me. Remember, the distance is equal to y2 minus y1 squared plus x2 minus x1 squared. Remember this?
Right.
This distance formula, right? Distance formula from geometry, and we used it some in pre-cal, but I prefer the Pythagorean theorem because this is just the Pythagorean theorem of points. Because I mean, look, what do we do here? Y2 minus y1, well, that's just, this minus this. It's just the vertical change, right? That literally says the vertical change squared. That's exactly what I did here. That other one says the horizontal change squared. That's just this. And then everything is the square roots just because I did this part. I just took the square root of both sides. So that's just a formula that is a direct consequence of this. It's much harder to remember. That is the Pythagorean theorem, just in terms of the distances that are changing vertically and horizontally. It's the same thing. That's how they got that formula, is using the Pythagorean theorem. Okay, so it's the same thing. If you plug all that in, you're going to get the same thing.
Would you not be able to use, instead of like making an extra triangle, since one side of that line is right, the other side is right, is it not possible to solve for,
Like, could you do this?
the town 20 miles east?
Well, you don't know that information then. Like, you don't know, like, the only thing that helps us here is that we've got both, well, I guess you have this.
That's what I'm saying.
Yeah, you could do that, that's fine. But I mean, that would be over here.
Yeah, I see.
You see what I'm saying? Okay. I mean, alternatively, this would be 2 and this would be 6. I mean, you could, but that would give you this. That's not what I'm looking for. Does that make sense? So yeah, I mean, you can solve for all these different quantities, but the only one I'm interested in is this hypotenuse. And so the only triangle I can make is either this one up here or this one down here. And they're the same triangle. It's just an extra step to flip it over. I mean, you can't do that. But do you see how, like, yes, you have these other quantities, but the one of interest is this one. All right, cool. What is it? Huh?
I can't do no more.
I think we're done.
Crystal more.
I think that's it. Let me scroll down and see. Yeah, I feel like we're tapped out at this point. Hey,
We should try it.
so again, this is why I was like, hey, please be fluent in that first section before we get here, because the purpose of that first section was for me to remind you of all the things that you would need for the real meat of what we're doing, which is this. It's pure application of all these different ideas. Like, you have got so many tools that you've got to pull out your toolbox here. There's one if you want to try it. Oh, look at this. There is another one. Yeah, I'm going to do this one real quick. This one won't take me long. We're almost done. Sorry. This one, you'll like this one. This one's easy, comparatively speaking. All right, so you're going to use a system of linear models. Hey, guess what? We just did that. To choose a rental truck company. So you got 2 rental truck companies. You got Keep On Trucking, and then you've got Move It Your Way. Notice you have 2 different scenarios here. You have 2 different, like, patterns. Keep On Trucking, and then you got the Move It Your Way. So I'm going to skip all of the other stuff, and I'm just going to go ahead and write a function for Keep On Trucking and the Move It Your Way. When will Keep On Trucking be the better choice for Jamal? Well, that means that Keep On Trucking costs less than the Move It company, right? Like, wouldn't you say that the better choice would be the one that was the less expensive? Isn't that what we're kind of looking for here? Okay, so we want the function k to be less than the function n. All right, so I'm just going to go ahead and write this. Upfront fee, that sounds a lot like an initial value, 59 cents a mile. That's the rate of change. We'll just call it X. And this one is 63 cents a mile plus an upfront $16 fee. All right, so we have K of X for keep it moving and M of X for the whatever other one is. So notice I've got 2 linear functions. Good so far? But I want K to be greater than M. That means I want the function K of X, less than the function M of X. I want the cost of K to be less than M. Remember that interchangeable thing I told you about? Remember I said that things are interchangeable when they're equal? K of X is just this. And M of X is just this. And that inequality doesn't change. We solve it just like a normal equation. So we're going to move all the stuff to the same side. We're gonna combine like terms. And then I'm gonna move the 20 over to the other side. I'm just doing basic algebra now. There ain't no magic going on here at this point. Okay, so let's do 0.59 minus 0.63. That's gonna be negative 04x. And this would be negative 4. What's the next step to solve? Yeah, divide. I'm dividing by a negative, so that sign needs to swap directions. So this would be 4 divided by 0.04, 100. Okay, so what's x again?
The cost. How many miles?
Yeah, miles. The cost is the output. So x is miles. So notice how I put that context back in. So when will keep on trucking be the better choice? When he exceeds 100 miles. So if it's less than 100 miles, he'll pick one, and if it's more than 100 miles, he'll pick the other. You notice how I just made that translation of what does X mean in this situation?
So at 100, they're equivalent.
Correct. So if he surpasses 100 miles, he should change over to the keep on trucking because he's going to pay less overall. That's it. Now we're done. You absolutely can. I'm going to give you your exercise set, and I'll have the section exercises typed up